Hello. So I am back. It's very soon. Why? Because I streamed at least two parts today only, and unfortunately, the voice was not there at all. So I think I have to record it again. Well, it's streaming, so yeah. So we just revised first of all where we left off in our second stream, which was array and slices. We sort of went through it, and we then covered all these types through aliasing and all. But now we'll target to cover this the whole conversion and all, because when I started the stream earlier, it was easy, but not that much, but still it was easy. And the examples are very small, and the concepts are very key concept, but still very small concepts. So we can go through them very easily. We can just sort of speed run through them in this night. All right. So we'll start with Rust by example. I have made a new custom folder, sort of, where if we want to, we'll just practice our code. We'll not disturb our directory structures or anything like that. So let's revise this. We left off using array and slices. So now array is the collection of objects of the same type, which is t, and stored in a contiguous memory, contiguous side by side. And arrays are created using brackets, square brackets, and their length, which is known at compile time, is part of their signature, which is t, and we send length. So t is the type, the array stores all the numbers, signed integers of size 32. We say it is I32, and the length, let's say it's 5. It's 5. So that's how we assign an array in Rust. As for the slices are similar to arrays, but their length is not known at compile time. So we send their length at a sort of runtime. So it is in a heap memory. So instead, a slice is a two-word object. For the first word is a pointer to the data, and the second word is the length of the slice. Now the word size is the same as U size, determined by processor architecture, like 64-bit or on a 86 64-bit machine. And the slice can be used to borrow a section of an array and have the type signature, that is %t. Now this is slice. Now we are importing a standard memory library from Rust, like we use it in C, like we use hash import, something like we use import in Python, and import in what, Node.js. We use include in C, so we are using use in Rust. So this is importing the standard memory library, and what we are doing here is we are creating a function named analyze slice. What it's taking is a slice. This is a buffer or variable, and it is of type reference type of an array. All right. Now we are trying to print the first element of the slice by indexing it with slice 0, and then slice has how many elements. We are then covering out sort of covering it by making a function called length. It already exists in Rust, like Python has length function. Uh, it's a function or sort of a mod. Nobody really knows right now, but yeah, it is there. It is available. You can just do slice.length and you will get a length of that slice. Why? Because, well, mostly arrays have these length assigned to it. As for the length of slice, well, it gets determined. Now we are creating a main function. Inside that we have a array, which is, well, variable is access. And how do we know it is an array? Because we see this type determined inside a square bracket. So first thing we see is a type I32. It means all elements inside this array will be of type I32, which means a signed integer of 32 bytes, means 32 bits means 4 bytes. All right. And there are 5 elements, and you can count, there are 5 elements. Oh yeah, now there are 5 elements. Now all the elements can be initialized to the same value. So like ys is, let's say, another array which is again of same I32, and it has 500 elements. and we are initializing all 500 elements to the value of 0. That's what we are doing over here. So it says all elements can be initialized to the same value. So in this array, all the elements have been assigned a value or initialized with a value of 0. Now what we are doing next is sort of indexing starting from 0, and we are printing over here first element of the array, which is x's, and we are printing the first element using index 0. So it will print 1 for us. And then there is second element of the array, which is x's 1, which is index 1, which is this. So index goes like 0, and then 1, 2, 3, 4, and length minus 1 always. Now there is another thing that we are doing over here. Length returns the count of element in an array. So in this array, there are 5 elements. So it should return, 5. How do we know? Because we have mentioned it. It is of size 5. In this array, it is of size 500. So yeah, we do know. As for what happens under the hood in this length sort of function, we don't really know the implementation of it, but we sort of have an idea that it takes this size of it and sort of tries to return it after some error checking or all. So next we are seeing, we are printing again array and occupies how many bytes. Then we are using that memory size of value and passing it a reference of access, which is again array. We are passing it a reference of array, which calculates the size of value or how many bytes are there. Since let's calculate it. Since it's I32, which means 4 bytes per element. And how many elements are there? There are 5 elements. So 4 byte is for one element. There are 5 elements. Unity method, just multiply them. We got 20 bytes. 4 5s are 20. So array occupies 20 bytes. All right. We'll see the printing message over here when we sort of run it. Shall we run it? Yeah. Now we are seeing print ln, which is sort of trying to borrow the whole array as a slice, and we are sending it in array slice, the reference of array access. Array slice was a function we defined over here, and we are passing it the reference of an array, right? And then we are trying to print the borrow the whole array as a slice, and we are printing the whole. We are not printing it right now. We are printing it over here. No, we are not printing at all. Yeah, we are not printing array slices, but we can if you want to. Now slices can point to a section of an array. Let's say there is array ys and we are pointing to first element and fourth element, not including fourth element. If we wanted to include fourth element, we would have written something like equality. Yeah, this works somehow. This works. So it now means that including the fourth element. Right now we are just taking it as in range. So this is the not the first index. First is the 0. So we are taking it from the second to sort of less than 4, and we are analyzing that slice, passing it on the function analyze slice, and we are getting it. So let's read the comment first. Slices can point to a section of an array, and there are a form like starting index and to the ending index. Starting index, the first position of the slice, and ending index is one more than the last position in the slice. All right, and if we do equals to, it means ending index becomes the last position of the slice, not one more than. All right, so we are again printing that borrow a section of an array as a slice, and we are doing this. We are borrowing it, but only the slice, not the whole array. All right, so here we are seeing some examples of slice, which is again sending a reference of an array. We have an empty array, which is sort of type u32, which is unsigned integer 32, which is 4 byte again, which has 0 elements to it. And now we are initializing it to nothing. Yeah, that works somehow. This is an empty array. Now we are asserting an equation or something like that. We are checking that whether this empty array, if we do this something with empty array, do we get this as a return? And If we do get, we'll get nothing printed over here. There is no dramatic effect from this assert EQ. It's not like print ln or something like that. It doesn't print anything. And if it does print, then there is some problem to it. And then there is second statement, which is more sort of verbose, because we can see it's passing sort of reference to the array, and we are taking it in a form of slice, but we are not mentioning the starting and ending index, so it takes the whole damn array. All right. Now array can be safely accessed using .get, which returns an option. This can be matched as shown below, or used with .expect, which is sort of a borrow. Borrow? Is it borrow? We'll see in upcoming detail. So if you would like the program to exit with a nice message instead of happily continue, we can say like this: for I, which is an sort of, what is it, iterator, I in 0 to xs dot length plus 1. So we are going out of index, you know we are intentionally going out of index. So oops, one element too far. So it will say slow down, you are going one element too far. All right. So this is a match function. If you have not seen it earlier, I have seen it multiple times now. So I know this is a match. It matches this case, which is access.get, which is I. And then if this I or this value matches to some value, then it will give us this print statement. And if it matches to none, then it will give us this message. So if the I, which was the iterator, gets some value from x as some value, even some value, we'll get this. So let's say if index, the last thing that it can get is 5. After that, it may not be able to get any sort of value from x's. So what it will show is slow down. You're going how many index too far? It will be printed over here because we are printing the I. So if it goes out of bound, indexing on an array with constant value cause compile time error, which is like this. And out of bound index on slice cause runtime error, which is like this. All right. So we see all the nice cities, and we are seeing that slow down 5 is going too far. And we can also intentionally, since we are doing it, we can also increase some more. Oops, one more element. All right. It will give us few more or 6 more, I guess. Nah, 5. Uh, all right, it timed out, but no need to worry because it works. I checked it out. It works. See, so slow down. We are getting sort of 5 more statements that you are going to index 5, 6, 7, 8, 9, for which the value does not exist, and array is also not of that much of size. So it can only go till here, but we are going beyond that intentionally, obviously. So we already studied it in sort of live part 2. Now this is our live part 3. All right. So earlier live part 3 and 4 will get deleted and it will be compiled into one. So yeah, that's what is going to happen. So we are seeing some custom types. So Rust custom data types are formed mainly through 2 keywords. So first is to struct, which is like we have seen it in C. So it defines a structure. As for enum, I don't know if I used it ever in C, but I think it existed, or I don't. But enum definitely exists over here. It means enumeration. And how we do it is, if something is defined in enum and we are using it, it's all right. But beyond that cases, we must exhaust the whole case. So it's sort of exhaustive in nature. And beyond that, it sort of doesn't know anything. The another thing it does enum is sort of, if you say add inside enum called calculate, then it will create a calculate add, which will be different from the Rust add. So you have to care for the implementation details, and if you're keeping it the same, then you might get a duplicate in your binaries, which is which will make it bulkier if it already exists. If it doesn't, good for you. You're creating your own type. Enum also gives you a great control over what you want and what you are creating. As for struct, it exists. We know it exists. We use it very widely, and we all know how to use it. As for constant, can also be created via const and static keywords. So we know that, well, we studied it in this, part 3 and 4. But we know now that we can create const exactly like C or Python or any other language. Like we mention it const, we specially use the variable name in all caps, like all capital uppercase, so that we can just see it and know that this is a const, and this is sort of intentional. You can also write in small case, but it is not recommended. If there is some constants, you want it to be glaring, highlighting in your program. As for the static keyword, uh, we have seen it multiple times, I guess. We'll see it in these programs too. So first of all, we are starting from structures. So there are three types of structures, which is structs can be created using the struct keyword first, which is tuple struct, which are basically named tuples. And then there's classic C structs, which is, I don't know, it'll load something. C struct. So what is C struct? So C struct is this. We are defining my structure, and it has type 1 member and then type 2 member. This is C struct. This can also be implemented in Rust. Exactly same. All right. And there is date. In that date, we have year, month, and day. This is our own structure. In a birthday, there is, let's say, character name. Let's say whose birthday it is, and then the date or DUV. As for the person, if there is a person, what is the name of the person, what is the age of the person. Inside that person, we can create another struct, which is which city he lives in, or what is the zip or address, much more. All right. So now this structure is called address. It is sort of a legal notion. See, you can use it. Now this is linked list. This is structure of your own, and type def is also used, but this is C and C++, and we are seeing the Rust, and it is not much different from that. So if you've used that, well, good for you. What this code does is, well, it hides some of the warning that you get for using unused codes. So we'll see that. As for what this does is derive debug, we know, so that we can use the debug implementation to print out stuff, and we'll see it in pasting it in our IDE. Then we can see the glaring difference while we try to. I changed my IDE to sort of Vim, my own custom Vim, because NeoVim had Copilot and I was not able to disable it. It created a lot of problems, so now I'm on Vim. As for NeoVim, it also exists, but I'm not using it right now. All right. So what it does, this allow, this, well, it says deny. Actually, it says deny because this is not signed and this is allow. So not allow means deny. Yeah, this is what we were getting every time. So we have to dismiss it. So yeah, this says deny dead code. So if there is any dead code which is sort of unused code, so deny them. Don't show us the warning. That's what it is telling us. So how about we just, for now, just comment it up. As for the others, we first read what is going on. We are doing this so that we can debug, use it in debug and print it out. So there is a structure called person, and then there is a name which has a type string, and there's a age which is type U8. U8 means 1 byte, but it is unsigned. So it can only be positive, no negatives, because age can only be positive. You can't be a -1 years old. All right. And then there is another structure that we are creating, which is just a unit structure. What it does, what it doesn't, don't ask me yet. Then there is structure called pair, which has I32 and F32 as its input. And what it does, No need to ask, but this is a tuple structure. Why? How tuple starts? Remember that? It starts from, parenthesis. If there are parentheses and there are two values, three values, multiple values, it can be of same type, it can be of different type. So here we are seeing that first value is sort of I32 types, whereas the second value is F32 types. All right. So this is what struct pair is doing. As for struct point, yeah, there is also struct point, which is now getting X, which is of type F32, which is float 32, which is 4 byte of float. And then there is point Y, which is again F32, same type, commas, remember them. Now, there is a structure called rectangle. What it does is stores the point structure inside top left and again the point structure in bottom right. So every top left, this top left will have x and y coordinates. This bottom right will also have x and y coordinates according to point, because point is also structure. So we have seen in that Wikipedia page that we can use structure inside the structure, sort of nested structure. So this is what we did over here. All right. So now we are coming up to main. This is the longest program that you will see in this sort of part. All right. So now we are in our main and we are seeing something like name is equals to string from Peter. So Peter is a string assigned to this variable name called name. And then there is age, which is 27. And now we are sort of passing those two variables inside the person and we are assigning that to the Peter. So tell me one thing, what happens to this name? Can we use it over here to print the name? Well, the answer should be no, we can't. All right. As for others, let's do it. First of all, just try compiling it. Then we'll make our own changes. Just see one.rs. So we are just getting warnings because we removed that deny dead code, so at the starting of the code. And now if we run it, it runs. We see there are dog barking quite a lot. All right, but we see various things happening, and we are seeing there's a person which is Peter. There's point coordinates over here. There is second point coordinates. Then there's pair 0, 1 and 0.1. Then there is another pair which is 1 and 0.1. So we don't have to mind them. What we are looking for is our own change that we make, and we want to see some errors happening in the real time. Don't mind these. These are just, telling me that I did not made it into a structure using cargo. I just made it a raw Rust file. So yeah, that's what it's telling me. Rust analyzer, reload workspace to reload. So what we wanted to see was if we used name and now here, will we be able to print it? So I think we will not be able to print it. Why? Because now name has already been transferred to the person which is Peter. All right. So if we say print ln and we try to print, let's give it a name. All right. And we say print the name. Will we able to print it? First of all, don't miss semicolon. I missed it so many times. But yeah, let us see. And yeah, we get an error. We are seeing that not found in this scope. How? We just saw that name exists. We just saw that name exists and it is in the same scope. Like name is over here and name is over here. So what's happening right now? First of all, this type of thing. Not found in Acha. So print L1, it was not found in the scope. All right, let's try for the name. Let's see error. All right, not this. You want to see errors. error happening right now. So we see a error, a long error this time. So we see the name, the whole code, the whole code first of all, and then we see move occurs because name has type string, which does not implement the copy trait. That's telling me that name cannot be copied. So it has moved where? To this place. Value moved to here. So it is now person.name, which is peter.name. We can access this name, but not just using name because name has transferred. As for if we try to, print age, will we be able to print it? Answer is, well, guess. It's a good guess field. So we'll just say we are now printing age. It should be also transferred. No, but surprise is that it happens not. It gets printed because age can be copied. All right, we just get a warning that we were getting earlier. Now if we try to print it, we get age is equals to 27. So we are able to access it. We are able to access the age, but we are not able to access the name. Why is that the case? What is the reason behind it? So we have read somewhere. I don't know if I read with you or I read with my play challenge. I don't know that, but I understand that this name, which is a string, is sort of a pointer. All right. So pointer can be moved, can never be copied. So its pointer moved from pointing to the variable name to sort of peter.name in a structure called person. So Peter is of type person, which is a structure in itself, and it has a, you know, it has a property or sort of a inside variable which is name, which has been assigned a name. Now, this Peter, which was a variable, which was a string or assigned to a variable called name, has moved, has transferred its ownership over here. But what happens to the age? Age is just a number. Well, it is. All right. Age is just a number. But in this case, well, Rust can just copy the number. It does not transfer the ownership or anything like that. It is not complex. Age just gets copied over here. So age is also there. If we say Peter dot age, we get the age. But important thing is we can also just access age normally, like we should be able. And there is nothing that has changed except the name, which is why we know that string moves or transfers their ownership, and they need to be borrowed if we want to just use them mutably or immutably, both. But age or the numbers can just get copied. Important point, very important point. As for, we try to print it using sort of uh, peter.age. Will we be able to do that? Let's see. Peter.age. Will we be able to access it? I don't know. I'm hoping so. If we did some error, just tell us. No errors. So the output will remain same, but that's what the great part is. Great part is that we were able to correct it. We were able to access the age from both, from here also, where this value 27 was copied from here. So we can also access this original thing, and we can also access this peter.age thing, which is in value wise same, but structurally where they live, what happens to them, totally different. All right, this is peter.age, and this is just the age. Since it was not a string, it did not move or change its ownership. All right, so this was important. As we what we did over here is just print the debug structure that we already saw, sort of a JSON format. We saw that there's a person structure called person, and name is Peter, age is 20, 25, or whatever, you know. Yeah, we saw it over here. This is what. If we just pretty print it, it becomes pretty JSON. That's all. So let's move on. How move on? We see that there is now another data types, which is sort of a point. So point is a data type in itself, but now there is a variable called small, this small point, sort of, small p, so point. But this bigger p, this point is sort of a data which has two sort of things inside them, which is x and y. So you have a called point, you have to pass the x value and y value. So here we are saying that there is a variable called point which has a structure which is point, and then we are assigning it a value of point x y, which is 0.4. And now we are assigning, sorry, we are making or letting another variable called another point which is of same type, point, same type, and we are assigning it a different value, that is point x, that is 10.3, and y 0.2. Now there are two different points which are of data structure type point. Like there are type string, there are type integers, there are types unsigned integers, there are type chars, or there are types booleans. So now this is our type that we defined, custom type, which is a point. All right. Uh, Now, what will happen over here is we will try to print point.x, means point, which is this variable, dot x, the value inside the x. We'll get this, all right, as it's the same as we, used peter.age to access the Peter's age, which is 27. So we'll get this point.x, we'll get the point.x. As for point.y, we'll get the point.y, which is 0.1. We print them, we are happy, we go home, we sleep. All right. I should open that, sort of output side by side. Yeah, see here. So we are printing the point coordinates 5.2 and 0.4, exactly like this in a bracket. So that bracket is our own, that we have given it in the print statement. All right. So now we are doing something interesting. We are saying make a new point by using structure update syntax to use the field of our other one. So we are saying, what we are saying is we are creating another point type structure which is bottom right. We are not defining it is a type point. We can define it. It's not very syntactically rigid. Like we can define what type it should be. We can just let it remain. We'll just let it remain right now. We don't want to see too many points on our display right now. But bottom right is also a type of point because we are assigning it a value of point, and the x is something that we have defined, that is 10.3. As for y, we are getting it from another point. What is another point? Another point is over here. And we are getting the y value of this another point. Well, this seems magical. This looks magical actually. And that's what exactly happens right over here. We get a bottom right. If we try to print it, we have a bottom right structure that is of type point, and we have a value of it as 10.3 and 0.2. So it's exactly like this another point, but its variable name is bottom right, and we have defined it by our own hands and using another point's y value in the whole output. All right. Now the bottom right dot y will use the same value as another point dot y, but due to some fate, it is also sharing its x value. We can just change it. It's in our own hand. All right, but let it remain. This seems interesting. Or let's change it. It's our control. It's in our control. So bottom right dot y will have the same value as another point, which is this another point dot y, because we used that from another point. All right. Now if we try to print second point, which is bottom right dot x, which is 100 over here, and bottom right dot y, and if we try to run it, can anyone guess what will happen? Well, everybody can guess right now, but just play around. Don't show me you've run sort of out of error. Yeah, it timed out. So as expected, but see here, we are seeing the output, which is second point, that is 10.3 and 0.2, exactly what we expected. We changed it to 100, so let's do it over here again. We change the point to 100. Where is it? Bottom right, yeah, somewhere near over here. What happened here is it got automatically sort of formatted by my formatter. So we'll see. There is just see. We're not getting any errors. And now we see the second point is updated 100.3 and 0.2. All right. Now there is second point, which is exactly we saw over here and exactly the same value that we expected it to be. Now we say destructure the point using the let binding. What does that mean? That means that there exists something called point and we are using its value to sort of assign it to another variable called point and assigning it to its x and its y's value according to this point, which is again of type point. Confusing, but not very much. Destructure the point using let binding. So we are destructuring this point using this let binding. So there's a point which is again getting the x value, y value from another this one, another variable that was earlier made named called point. Now we are creating another data structure that we already have, which was rectangle, and we are creating the what do we call it? Rectangle is a data structure. Yeah, and this is a variable, so we are creating a variable since it is unused, so we have appended it with underscore. That's what we do if we are not using it anywhere else in this code. So instead of getting warning and shouting at us, please do this, do that, we just undersign it, use underscore before that, so it will not shout at us that this variable was left unused, this is dead code or whatever. So we have a variable that is rectangle, and that type of the variable is rectangle, which is our own defined structure, and we are passing it a top left value and bottom right value. Point is x left edge and y top edge. What is left edge and top edge? Let's see. It must be over somewhere here. We don't see anything like that. Structure instantiation is an expression too. Instantiation. What is this? Instantiation. Instantiation. Initiation of the instantiation. All right. So there's yeah, there. This is the left edge and top edge. So we are getting this value from here and we are assigning it to top left value, and then we are using bottom right over here, and we are assigning it to the bottom right value, which takes the type point. That's how we define this structure. It is of type point. Top left is of type point, bottom right is of top type point, so it can only take type point and it will be also of type point. As for instantiating another sort of structures, that is unit structure, we are instantiating it using this underscore unit, because we are not using this variable any other places, and we are saying this is a unit which will just return the unit type, which is the unit type. No, unit type is this parenthesis, this unit type. All right, which is empty tuple. Empty tuple is unit type. Parenthesis has a value of empty tuple, unit type. Now we are instantiating a tuple structure, which we called, pair over here. It has two values, I32 and F32. So 4 byte integer and 4 byte float. So we are passing 1 and 0.1, valid, totally valid, and we are storing it in a variable called pair. Data structure is pair that we define for our own selves. And then we are printing the pair contains this and that, which is pair.0 and pair.1. These values over here. Let's see. Pair contains 1 and 0.1, exactly like we expected. And then there is something called pair again, let pair, now capital P, not small p, which is again dereferencing this pair to this again. So it will get the same value. It's just we are first of all instantiating it, and then we are seeing some destructure or dereferencing the pair. So we'll call it destructure a tuple struct, destructuring a tuple structure. All right, seems nice. The same value and everything seems nice. Now these two activities are not fun at all. If I start spending my time on it, I'll spend it. So I sort of made these using my whole brain, and I don't want to use it right now, but let's try. What's the point of it if we don't even try? First of all, copy this cp1.s as one.rs, and then you'll just use one.rs for editing out. We remove this. We don't want to get much of an error right now. Allow it. And then what we want, read carefully. There is a function which is rect area. We have to create a function, not a structure, a function, which calculates the area of a rectangle, and try using nested destructuring. Nested destructuring. So let's create a function. Where should I create this function? Let's create it over here. All right. Let's create a point. We create a function called, what is it called? Rect area. RECT, then area underscore in. What do we pass in them? Which calculates the area of rectangle. Try using nested destructuring. So to calculate area of rectangle, we need first of all a rectangle into it. So we'll pass a rectangle, all right, and then this must return us a type which is sort of F64. That's what we expect. But F32, let's make it 32 because we saw everything as 32 over here. No, it was all F32, 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 F32. It's all 32 bytes. Even points are 32 bytes. So we shall match that. And now what we have to do is create or return the area. Now we'll say that area is equals to, let's say, length into breadth. But now we can return this, but just explain what this length is and breadth is. So to do that, L is equal to, let's say, x2 if there is x2 minus x1 normal, and the breadth is, we have to use semicolon. We can't just return everything. Y2 minus y1. All right. Now we have not yet defined x2 and x1. So we will say that how to dereference. So we get rectangle, and we can say uh, let rectangle is equals to let small rectangle RECT is equals to, you know, has two values uh, like this. First is top left. So top left, and it has some values. And then there is top right, right? No, it has bottom right. VO, TTOM, right. HT, bottom right. All right. And we pass a big rectangle to it. RECTANGLE. Big rectangle to it. We got it. Now what? Now we'll say x2, first of all, x1 is equals to top left, uh, top left, not what? We have top left, and inside that we have point, which is dot x. So I either we can directly access dot x. If we don't, then we have a problem. Top left is of type point, and we have x. So x1 is this, and then we are doing the same thing with all the x2 and everything. All we'll yank it, we'll paste it. We'll say this is replace it with y, and we'll say replace it with y. XA, no need for XA, it's not XA. Right. Yeah. Then we are doing this for y2 again. First of all, give the semicolons, otherwise we'll forget them. We might mess things up. Y2 is equals to BOTTO, bottom right, and it's y. That's it. X2 equals to, you know, BOTTO, not right, no bottom right, which is a point, and has the value x inside that. So we are getting everything. Now this returns an area. So let's say here is a rectangle, and if we pass that rectangle through our function, which is rect area, should we get something, or should we not? Not like this. Oh, now we say let area is equals to, let area is equals to rect area, and we are passing a rectangle through it. So we have a rectangle which is small. This is whatever this is. Rect ICTALGLU, not two B's. All right. I am expecting that we should get a return that is of type area, and I want to print that area because it is of type F32. But let's see if we can print it out without getting any errors, because in the first try, well, there was not only errors, there was spelling mistakes, there was well, too much spells. Even I wrote, print, I wrote something like that. There was too much of a mess in the first try. But now we are calm, we are composed, we are trying to be more composed, because this is a second try and we have to do our best. Area, semicolon, don't miss semicolon. We are saying this is a area. All right. If we don't get any errors, it is not a lucky day. It says area is nothing, so first of all there should be let. If we have not let yet again, we should use let everywhere. Yeah, there's first of all many errors. What is x1? You should just let x1 be. Append, not tab. You should append let x1. Then you should let. I used too many variables right now. Earlier I did not. I just used and it took me a while. But I want to simplify this process as much as I can, and I want to make it modular so that it is simple. So let. Then we are returning the area. I don't think. Now what? Expected F32, but it found a void, which means implicitly returns this as its body has no tail or no return expression. But we just wrote the return expression, you know. Uh, we just wrote the return expression. Why is it not returning? Because we are assuming some steps. Just C for W. How about now? Is it still same error? Now there is something else. Error has shortened drastically. Now we see that there is type name. We must implement a type name. All right. So rectangle is of type. So rectangle is a structure in itself. So just say rectangle is of type rectangle. What's happening over here is this is a buffer which is rectangle, which will take an input of rectangle and it is of type rectangle. That's what's we'll see some less errors. No, we did not. Saying us to create this instead of, and it's also telling us expected line 88, expected and rect area, function rect area, expected sort of something. Did we not implement it? We just did right now. Let me see. There's a function which take, let's not confuse ourselves. Let's not confuse others. We can just make it rect, small rect, important, CW. I'll just rect. All right, it is taking the rectangle, which is of type rectangle structure itself. And we are not taking it by reference. We are just taking the rectangle. No problem over here. 88 line. I think this looks good. If it doesn't, well, then what will? I'll shorten. Rectangle. What it says? RECTANGLE. It looks nice. Line 92 says help use structure literals instead of rectangle. Top left val, bottom left val. Use structure literal syntax instead of rectangle. Let rect not found in this scope. Cannot find the structure. You need type rect in this scope. 89 and C. Let's first go to 89. Guessing this. It's telling me it is not expecting a rectangle. Yeah, we have changed the name now. Let's do this, right? Then we have the value and rect. Now it should not show much of error. You have assigned it, run it. Now there's more error, I guess. No, there's a listen. Not found in this scope. Rect is not found in this scope. We are creating it now. Did we not use equal to? Let's go to 89. Rect we did use equal to. So by how did we dereference it? So we are saying dereferencing it is something like this. We just directly get dereferenced, but not here, not in this case. Why? I don't know why. Uh, there's top left value first. Then there is bottom right value. We are dereferencing the rectangle. All right. This is what we are trying to do. But it's the same error. Says aborting due to one cannot find structure, variant, or union type right in this code. Behind, instead of saying small, say RECTANGLE rectangle. What about now? Yeah. So to dereference it, we must use the structure's name. There it was rectangle. Now if we run it, what was it? 1.rs, right? We should see area. Now why is this minus 19? First of all, very, very awesome question. Because we did minus, but we did not use mod. So to do that, I sort of implemented a if condition, I guess. But what's a better way to do this? So I said return this. So let's write it down. If you know L into B, so if greater than or equal to, or let's handle if less than uh, 0.0, then what we shall do is we should just say that multiply this whole damn thing by -1. Uh, return this -1 into L into B. That's what I did. And then let's handle else. It was saying, yeah, let's see, else just return L cross B, which is nice. Any errors? Yeah. What is it? No implementation for integer I is equal to. So instead of just multiplying 1, we can use minus 1.1. Where is 80, 91? Let's go. Instead of just using 1, which is an integer, how about we append it to, now it's a float. How about now? Is there any error? No errors. So let's go. Let's run 1. Yeah, we are seeing 19 is the area. Why? Well, the point coordinates are something like this: 5.2 minus 100.3, and then 0.4 minus 0.9 calculated. That's your area. So we are good to go. We implemented the first activity. Now the second activity is add a function which is square. Now which takes a point. Now the square is another function. All right. So let's create it. Create it how? We just move this. No need to move it. We'll use the same thing. 1. I just opened the binary. Oh, I written it. What if I wrote something binary? It works. What if I wrote something random in the binary? Will it work? It shouldn't. It should just break. Cannot execute. The execute format error. What if I just undo my changes? I can't. Oh my god. I don't, but I know that I made these changes. What about now? Will it run? Yeah, it runs. It's so easy to, you know, do something with your binary. I'm deleting something. It just there's no segmentation. What up? Don't mess with your binary. And now instead of using vim.1, let's vim.rs. And now we have to create 95. Let's go down. Oh, let's go up. Let's create it over here. We are creating another function, which is function, and name is square. What it does, it's very interesting. What it does is a square which takes a point and a f32 as an argument. All right, so it will take a point. Let me say it will take a insert. What is it? It will take a point of type point, and then it will take f32. That's it. And then what we'll do is return the rectangle, returns a rectangle with its top left corner on the point and width and height corresponding to the f32. So it wants the point, and then it wants the other side to add the point, and it wants to return what? Returns a rectangle. Yeah, that's what it wants to do. Sort of a rectangle, which is a square. That's why function is square. So let's define somewhere if we also have a point. Well, we always have a point. Over here, let me define something called square. Not like this. Yeah, over here, let's define something called let sq equals to something like square square, and we are passing a point which is point. Yeah. And we are also passing f32 value. So what is f32 value right now? Let's say 5.0. All right, this is f32 value. We are passing it, we are closing that, and then what we are doing is we are printing it using a back. You'll see something interesting like this is a square, and we'll go something like, yeah, give us value of square semicolon. We have an implementation of square. Now we have to just write the function which will return what? Which will return a rectangle. So damn it, it returns a rectangle. rectangle. It returns a rectangle which is a type in itself. Now we have to prepare for a code, but not like that, right? So let's get ready to return a rectangle. We'll say rectangle. We have a rectangle, and inside the rectangle we need two arguments. First of all, we need something like top left, which we'll say is of type point. We have a bottom right, UTTOM which we'll say is also type point. For now, let's create, instead of rectangle, well, let's create a line, just a line, and we are returning it. So we are getting a point. We are not even using the f32, and I guess we should be using small p, small p. right? And return it. I will see many errors, first of all, so be ready for it. Uh-huh. Yeah, so many errors, so many damn errors. What is the first one? Yeah, spelling mistakes. That's what I did earlier also. I don't know why I have some, dushmani with bottom. My bottom spelling is B-U-T-T-Y, but here it's B-O-T-T-Y. So this is correct now. Shall we see your bottom? There is still a long way to go. We are saying we are using assignment variable, colon. Is that how we always design it? Yeah, we always, no, this is type, so not always. Let me see how we, so this is a rectangle, which is type rectangle, and yes, we used this colon instead of everywhere. Let's use it on words. Replace it with colon and replace it with colon and come down. Word. Then we have another error. That is F32 should also have some name. Either F32 is a name or F32 is a type name, and we need a name. Let's add a name to F32. Let's say N. Let's say it's N. Right. So there's a point. Then there's a N which is of type F32. All right. Now we'll do something with this N. Let's see. There's some errors. Stuck point. Consider implementing clone for this type. Like you could clone this value. All right. What else does it say? It says cannot find function, tuple, structure, or whatever square in the scope. Help, a function with similar name exists. Notice the capitalization. Did we do something wrong with a function name? Let's see. Let's find capital S Q U. So we find two squares, and then we don't find, sorry, we find two squares, and then we don't find any more squares. So it means that instead of naming our function capital square, we named it small, capital S. See how dumb mistakes I made. So these are some of the dumbest mistakes one can make, but I'm making it again and again. Well, that's destiny. Not right now. We'll change our destiny. Now it is saying value here after value used here after. All right. So instead of using that value, we'll first of all now not this. It's like sure. So we'll say 0.1 is equals to point, isn't it? Return. Then we'll say 0.2 1. Instead of returning 0.1, we'll say 0.1. Instead of returning point, we'll say 0.2. Is it good enough? Let's see. Now there's more errors. Square SQ cannot be formatted with default formatter. So we cannot just, yeah, we cannot. So to print it now, we need to do something IT, and that is, use derive debug. Sort of like this. Square bracket DE RIVE, inside this VEBG, derive debug, we are good to go. Yank it, come down, and paste it. Still, we have not changed our formatting parameters. Let's go J J J J J. And, what we'll do first thing is we'll go here. Since we want to, print, we'll have to use debug format, which is like this. Then print the square, which will be of type rectangle. But all right, now what? Now there's a point. Where are we? There's a point one, point two. Inside that point one, let's make some changes. Right now, we'll say mm, point has two values now. So let's go in point and change its value. So point dot x plus n, and then we have a problem here. If we do this, we are like point two. Is also type point, so dot x dot x. If we yank it, we have to go like replace it by over here, replace it by, and instead what we can do, just how about just doing this damn thing. Will it work? It should, sure should work, but it won't. Why? We are cursed. Ah, so we are getting some help. Consider implementing clone for this type, or you could clone this value. That's what I tried. Now we are saying point is equals to point, and let, we didn't use let, did we? Yeah, we didn't. I remember we didn't use let. W, let's append, no, let point one, and then let point two. We are returning a rectangle. I don't think we need that. Plus, there are too many diamonds. First of all, n expected, one of the 8 possible tokens. Use of both value point. Then there is point, which is point. Is to move occurs between point which does not implement the copy trait. Another point is sort of just another point. Same thing. It's telling me to clone this value, but how? How did I implement that here? What are the cus? Okay. Let's do one thing. Let's take it one step at a time. So we'll say point one is equals to point, and we are creating that point one. All right. And here we are just defining it manually. The point two is, let's say, 5.09. Then this is 3.50. All right, it would work. No, still these errors. How about we won't even use points? So let's go to 90 GCC. I thought it should work, but it didn't. So let's go back to our own ways of doing things manually. 1.9067. All right. Let's see. What is it? 63. What is line 63? Where is line 63? So it says Y, stop edge. So what happened? And why do I care? Restructure the point using let binding. Oh, so we use point somewhere else also. Instead of doing that, how about we just, instead of passing a point, we pass our own manual point. How about that? D. 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 J. Come at 90 over here. Before this, sort of here, print it. Not like this. Print it. Yeah. Okay. Now in point, we pass our own point. That is, let's say, we're passing 3.3, and then we are passing 4 point. Will it pass? I don't think so. Let's hope so. It does. So we are saying x is this value, y is this value. Instead of doing this, let's create our own point. Instead of doing this, just did y like this, y b and c3w again here. We say let p equals to p to int point this, and at the end this is our point that we passed. All right, the p gets passed. Okay, this is our n, which is f32. So we are passing point b and f2. Now what? We are not using anything, so what's the point of it? Yeah, let's also make it seed point. Let's do it over here to see. Let's see for the errors. Right, don't use curly braces. To make an array, use, these are not arrays here. These are values. Should be like x, oh sorry, insert is this, and then let's say y is this. Come over here, down below. And let's say x becomes this. Now I think we're good to go. Less errors, but still some. So there is something on line 96 which says top left, which is this. So we'll say some structure, which is this is a structure called point. So we'll have to mention that this is a point. Same problem over here. So we'll say this is a structure point 98. Where are we? Yeah. So this is a structure called point point. Then back over it is a point point. All right. Can we pass this? Let's see. Only warnings and nothing serious. So let's see the square, which is a rectangle. Actually, data type is rectangle. So yeah, top left point this, and bottom right point is point this. So instead of point this, how about we used P? Now, since there is no error, we'll start making small changes. 98. Instead of sending, how about we just keep it here, but we'll copy, make it, paste it, uncomment it, do this instead. We say we pass it a point P. And we say that's it. Will you show much of error? You show that there is some errors. Like expected one of the 8 possibilities, like try adding comma or rectangle missing bottom right. Or it is not missing bottom right, it is there. So I guess I used semicolon, which is wrong. Should have used comma. That's what is suggesting me. Word. Replace it with comma. No errors, I guess. Yeah, no errors, only warning. And if we try to run one, we get 3344, which was our point P. Yeah, let's go 98 point P. Things are happening, things are falling into place. Want, a point 2, which will have the same value, but uh, just that its x value will be plus whatever the n is. So here we are saying x value will be w. Change this whole damn thing. X will be p dot x plus n. Is that allowed, or will it say that it is already used or something like that? I want to see p dot y plus n. All right. There should be some errors. Yeah, but small errors. So value used here after move. So what is it? Top left P. So value moved over here. We can't use it. Move occurs between P and point. So instead of moving the point, how about just taking the reference of it? How about that? 98. I just want your reference master. How this? And how about doing this? Will it work? What is it? Value borrowed after move. We can't even do this very well. P has type point which does not implement the copy trait. Value mode over here. All right. What I am thinking, let's do that. What I'm thinking is bring that P down somewhere. Let's say over here. This is point 1. But instead of taking point, we'll say it is point. We'll say this is point, let's say CW. Change this to CW. What is it? CW. Yeah. Let's say this is X, and we don't want anything except we want value from the point, and we recreate it, paste it, But instead of X, we say that, we want Y. So replace it with Y. Go with your instead of Y. Instead of doing all these and then, and instead of passing P, we remove this, which is by DD. We make it like this. We say, all right, copy this instruction. We're not liking this, so we just say C and so landing, comma, and same for this C and everything over here get structured. So when I open it up, see, oh, it didn't get structured. No worries. So instead, we'll insert P over here. It is Px, and this is Py. All right. So now we'll say X is Py. Insert Py. Where is it? What? Append. We'll say something like it is Px. Then this is Py. All right. What will happen? No errors, I guess. No errors. We used it perfectly. So now we'll go back and we'll say over here too. We'll say X is also CW. Deleted it. Px. And let's say this is, since this is a number and borrowed, it gets copied. So now it is Py. But yeah, you don't get any errors. Since it is a number, we can just do arithmetic on it. So instead of, just saying that, how about now adding n to it? Insert, add, n to it. Go over here, add n to it. No errors, I guess. Or do we get any? We don't get any error. And if we try to run it, we get a square. It is a square whose length and breadth are the same. We're doing x2 and x1. We'll make the point simple. We can just do that because it's our point. We've created it. Instead of saying 3 by 3, it will say 1.0 about this. Nice. All right. Again, it will say sort of how much? Let's say it will say say 5.0. All right. No errors. Run it. Now this is 1, this is 6, this is 5, this is 10. Minus it. It is 5, 5 square, obviously. So minus 1, 5, 10 minus 5, 5. We get a square. So now we are taking a point, we are sending a n, and we are getting a rectangle as the return value. Top left corner on the point, we have a point, and top left corner is on the point, and the width and height corresponding to the F32. We just did it by increasing the bottom right corner. So let's move on. That was the hardest fall. As for these, let's see what are these. Yeah, it's simple. I think we have not moved forward yet. Yeah, we are still there. This took a lot of time. It was across approximately 3 hours or 3 hours 30 minutes long. and after that we have to spend somewhat around 2 hours more. So total 5 hours, and we have only spent sort of 1.5 hours. Yes. Now we are on enums. So what are enums? So enum keyword allows the creation of a type which may be one of a few different variants. So any variant which is valid as a struct is also valid in an enum. Now the both structs and enum are a custom ways to create our own sort of structures in Rust or C or any languages. But enum is sort of a enumeration. It's what is enum? Let's search it. We'll get a result of enumeration. Enum Rust. Right. We can search it that way. We can use AI. We can use Google. We can use anything that is at our resources. There is, I guess, some network errors. What? So enum is a type that can be used, that can be one of multiple options, but importantly, it's guaranteed to be one of those options. It guaranteed to be one of those options at the same time. It's complex over here. Now, in Rust, an enum is short for enumeration, is a custom data type that we create that represents a value that can be of one of several possible variants. And each variant can optionally hold associated data, making enums powerful for modeling complex data structures. All right. So let's say there is an enum, and inside that enum, we named that structure web event. Inside that, inside that enum, we created few of the functionalities of few of our data structures of our own. And outside these, nothing can be, used. Nothing. And inside these, it will help us sort of custom hai, so it will help us get more control. We can make it and directly control it from here. We don't get much of errors and multiple facilities. Create an enum to classify a web event. That's what we are doing over here. Note how both the names and type information together specify the variant, which is page not loading is page unload, and key press, which is char, and if not is there, then paste string. So that's how things are working somewhere here. Let's see. Each is a different and independent event. So there is a web event. It is our data structures, like we created, rectangle, square. Oh, these were the functions. No, we created point, unit before that. So yeah, here we are creating web event, but inside that web event, we have few things like page load event, and an enum variant may either be a unit like. All right, so it's a unit in itself. Then there is page unload. If page doesn't load, it is page unload. Then there is a like tuple struct. So key press is a tuple struct which has a character. Tuple can have anything. That's why it's tuple. It's very sort of dynamic in itself. So we have a key press which has a type a tuple character. In character we can have A, B, C, D, E, F, whatever character. All right. There is a paste which will take a string. Let's say, hey, I am a pasting string. So let's say something like that, and it will do something with paste. And if there is C like structure, then it is like click, and then there's point which is type I64. Then there is Y point which is again I64. So what do we do with this enum now? We have created these web events, but what do we do with it? So now we can just match the whole event, which is a web event type. So we have defined a variable event inside a function inspect. So if there is a function inspect used, and if we pass any web event through it, it will just assign it use event, which is of type web event, to compare what sort of web event is happening. And then according to that match, we can take actions. So here we are just printing sort of stuff, but we can take literal actions. Like if it says add, we can just use a plus b and it will return that value. See, no semicolons have been used. Otherwise, that would have just become a normal statement. Separate values. These are not, uh, stopping it from returning those values if it matches the case. So let's say there is a inspect, there is a function inspect, and we run a event that is page load. We will matches event matches something called page load. So this thing will start happening. So from web event, we have a page load and we will print page loaded if we get an event like this. If we say page unload, then we'll say page unloaded. So it matches the event, and according to that match, we have used match everywhere now. We have used it in C and everywhere else. We match it and we do the following actions that we want to. All right. So what now? Now there is a main function, and we are simulating those events, and we are trying to see whether they work or not. So we are creating a variable called pressed, and inside that we are making a web event happen, and we are pressing, sort of simulating a key press of X. Now it should say something like pressed, and the key is X, which is a character. So it will say pressed and X, and then over here it says pasted, and we try to simulate web event paste. So it will say something over here. It will say pasted, and whatever that string we are passing, my text and the to owned. This is sort of borrowing. To own sort of creates an own string. So this is our own owner's string. We are the owners of this string, the pasted is. All right. We can directly say toasting or something like that. But yeah, the pasted is sort of the owner of this my string, I guess. And we are using that to click this match event. It is matching that web event paste. Who matches it? It does not. It does not. It does not. It matches, and it passes this print ln pasted, and whatever that string is, it says my text. And after that, we are simulating click. So we say click and x20 and y80. That's what we do. If it says page load, then we say, yeah, page loaded. If it says page unload, we say page unloaded. That's what we are simulating, and we are seeing that match event happens. And it does not go beyond this web event. If it does, we have to define it. We have to make this, enum exhaustive in nature, and we have to make this match also exhaustive in nature. We also have something like, underscore, which matches all the remaining values. Let's say if we did not imply for click, we can just use this underscore. But this becomes dangerous very soon, because we don't know if there is any error or not, or then there are any you know, side values or not. We are just passing it through underscore, and it will pass for some time until and unless it starts creating some errors, and those errors will be dangerous. So we must always make it exhaustive so that there is no scope for error, and we should always match every sort of exhaustive events one by one, or some sort of handling to it. Either if it returns error, we should even handle sort of a result or something like that, so that it can also return error, not just the result. So there's another syntax which is inspect, and inspect is also inspecting the paste. Inspect is also inspecting pasted, click, load, and unload. These things, I guess. Inspect shouldn't send us some, should not respond to us, because if it does, then there are some problems to it. All right. And if it doesn't respond to us, then everything is good. Vim do.rs. Wait, pasting it. We are running it. How? That's C and do.rs. We learn do.rs, and yeah, we pressed X. There is my text. This is coordinate, page loaded, page unloaded. That's what we did now. Yeah, that's what we did. So it's the same thing. As for inspect, these are just inspecting it. So if let's say some error occurs, how about I simulate some error like page unload? What if I spell it wrong? Very small error, but let's see if it catches it first. Inspect, or our compiler does. because compiler of Rust is also very less prone to error, so it might just catch shit. Or yeah, so our compiler does not allow us to sort of do that. So we say you. Oh, instead of that, how about I just remove it from over here? Instead of doing that, how about I just comment it out? Now what? This is not even inside the inner. So we are getting errors. All right. I guess we won't be able to do that. So how about I make some mistake in the inspect itself. You know, inspect is this function. Inspect, and we are passing the pressed to this, and everything is happening. So we say pressed is this, and pressed goes over here. We do everything over here. Uh, let's try some create errors. It always helps us that there exists a click, there exists a where we would. But I don't think I can simulate an error right now. I cannot. Word, word, search, word, click, go. Let's not try to, force the error. It does not happen. Does not happen. All right. Now there is type aliases. What are aliases? So let's say if this thing's name is damn long. Like, how do you even speak this? Very verbose enum of things to do with number. Are so we are just adding and subtracting. We can just call it, calculate or operations, something like that. So now instead of calling this enum every time, this like the web event we called over here, we called web event everywhere because we need to. That's how we know we are using this type. But instead of calling these long strings everywhere, we just create an alias where we assign sort of alias this value to a string or to variable called operation. Now wherever we call operation and add, it goes over here very verbose enum dash 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 and takes this add and you know works with it. So this works. We can also just use this very long thing and it will also work. So no need to worry. This can always work. So let's do this. Let y is equals to, instead of operation, you want to use the real deal. So let's use it. No need to worry about subtract. It will subtract. It is the same damn thing. It's just writing it is too cumbersome and we might easily make a mistake. So instead of doing this, we are using a type and creating a alias for that. All right. This is the most common. So let's read this. If you use a type alias, you can refer to each enum variant via its alias. And this might be useful if the enum is too long or too generic and you want to rename it. And so we just renamed it. Not going and changing this, but just aliasing it. This is also something very useful that we do over here. Let's say I have a function called ls, which is normal, all right? But there is also something like lsla, all right? But calling ls dash la, I think it is very cumbersome. I don't want to, ls then dash la or la, not doing this. And I sort of made my own alias for this. I just made ll. It is not an official program. It does not exist. I made it. It's an alias in a bash RC script. So it is like this. All right. If we just grep from our, small cat, what is our bash RC dot bash RC? And if we grab sort of ls, we can see, we can see, don't see this, but see the alias. So ls is something like color auto, it's automatic, but we are also adding color. And then there is ll, this is also alias, which is of type ls-l. And there is la, which is ls-a. And then for hidden, only hidden, so we will say lh. If there is any hidden bytes, we'll see them, but since there is not, so ls cannot access, no such file exists in this directory right now. So but lh can. So we have created our own alias. This is very similar over here also. So instead of calling this again and again, we just rename it or just create an alias for that, and we call it by this name. So now instead of doing ls dot dash l or la, I just do ll, which is very common for me. And it works because it's just an alias. As the functionality, it remains the same. Full functionality remains the same. Now, the most common place you will see this is in IMPL, which is implication. Implication or implementation. Let's search. Let us search. What is IMPL? Not OMPL. IMPL. I think the net is quite slow, but no worries. Should work. And let me check something else for the time being. So yes, everything's working, and we can see right now. All right. So IMPL in Rust is a keyword used for implement functionality. So not implication, but implementation or implement. So we are implementing a very verbose enum of things. है ना? So we do this, and instead of aliasing it, we just use self. There is a function called run. Inside that, we pass this self. Self is this itself, and this self will pass what value? Let's say it will sometime pass add, sometime it will pass subtract. So it is self. Then there is x passing to it, which is i32 type i32, and there is y passing to it, which is again of i32 type. And then the return value of this function run will also be of i32. And what this function is implementing is, it is matching the self. If the self is of type add, if this has a type of add, then what we do is we add the stuff. If it is add, we add x plus y. And if it is subtract, this self is this, very verbose enough. This self is this. And if it has a type subtract, and if it sees the self has a value of subtract over here, then what it does is subtract from x minus y. This is a very simple thing. All right. So no need to worry about this. It is the simplest thing you'll see. Self is also a alias. So the most common place you will see is the aliasing is in implementation, sorry. Implementing functionality block using the self alias. Self is also alias, which is alias for this. All right. So let's move on to learn more about enums and type aliases. It worked. So it is showing some sort of consider adding a main function to this. Yeah, because main function is the starter point or the starting point of any programs like Rust or C. Without main function, mostly nothing works. Nah, now this works. And we are getting no output because we are not doing anything. Uh, what if we just did? What if in this? Uh, what if in this? First of all, use this alias operation. What if in this? First of all, take this, and then say, let's say, OPERATI operation. That is type, let's say, add. Then we are passing two values like 5, comma 6. Will something happen? Error happens because first of all, we are not printing anything. So yeah, and second of all, we are doing some mistakes like undeclared type operation. Why is it undeclared? And I just said that it is this. This is this. Consider importing one of those lines. Use generally operation or a steady operation. But I just want to add. What's wrong with adding? This playground is not working. Hmm. Add is not found in this scope. How about I directly use this? Will it find it? Hmm. What is it? Defined here. Call expression requires function. I guess. How about now? Hmm. This is interesting now. You might have meant use enums variant. Very expected value found enum. What is the error? That's what I want to do. How about I use just operation? OPERATION operations. First of all, if I don't get any error, then we can try printing it. But first of all, let's, you know, instead of doing this, yeah, I tried doing that. There was some error. This is add. What about now? Timed out. So how about just copy this, and if there is any AI, is there any AI? What is this? Yeah. What's wrong in this Rust? Yeah. Yeah. Right. You can tell me. Just tell me. Right. I understand. So what is it? Issue is that implementation block inside fn main. Incorrect method call syntax is wrong because add is an enum variant, not a function. That takes argument. To call the run method, you need an instead of enum first. Fix, acha, this is a enum variant, all right, not a function that we are calling like add. All right, so it runs like this. Oh, okay, okay. Now I understand what is happening. First of all, bring this main down. All right, where it usually works, just bring it down. Now it is at its usual place. Usual place. Now in add, we have a function over here. We have defined a function called run, which runs. And now it will, yes, run. It runs. So now what we can do is just print it out if we want to. So we'll say print macro, say this, and then this, and then comma, and then just run it out. Just run this something. Now it should print 11. Yeah, we got 11. So thank you, whatever AI model this was. The result prints result correctly. So it helped. So if we don't understand anything, just search it. Next, so there is use. So use is something that we have used multiple times, like. As we, what if we had to import, library called NumPy in Python? How did we used it? We imported it using import or using from library and then import. But we used import. Let's say Node.js, we have to import some module like WebSocket. What will we use? We'll again use import. So like these import modules, how about C? In C, we want stdio.h. How will we import that library or that header file? We'll use hash include. So in Rust, we use. So we have used it somewhere, if I guess correctly. We have used it to create, memory from standard memory. We used it something like this. We use to bring standard memory, if we remember it correctly. Yeah, we did it back there in the codes. So where we used size of file, yeah, that one, size of array. Yeah. So here, this first flag is not, and then it says allow dead code. So it means that deny dead code. So either we can write not allow dead code, or we can just say deny, deny, deny dead code. So what it does is suppresses any sort of warnings that we mostly get here. Here's the warning. I want a warning. This is not a warning. Is there a warning? Is there a warning in this world? Let's get a one. Yeah. So there are warnings like these. So it says help convert whatever. So if we add this, game $1. Yeah, we have added this allow dead code or sort of takes it and then CW. We said deny dead code. This works for the same. All right. It's sort of we are getting this dead code and we are getting name field in this struct. Field name is never read. Person has derived the implication treat debug. Intentionally ignored during the dead code analysis. Length level is defined here. All right. So this thing was suppressing, our errors that we would have gotten else. So let's suppress back it again. Let's suppress it back by not, and then CW sort of allow how it's worked. Just work for a long time. Yeah. So it sort of denies the error. All right. Let's use allow only because that works. Deny doesn't. I don't know why, but I used it. So this sort of prevents us from some sort of dead code or unused variable. So we'll see it in this code. We are seeing there is enum, which is stage, and it has two components to it, beginners and advanced. There is role, which is enum, two components, student or teacher, and then there is function main, which is explicitly use each name so they are available without manual scoping. So it says use, create, stage, then beginner and advanced. What it does is it makes these two things sort of global or without any manual scope. So we can use both of these everywhere directly by calling it beginner or by calling it advanced. Otherwise, let's say, first of all, let's try running it and then read it. Automatically uses each name inside the role. So every name inside the role gets here because we have used star. So every name inside the role, create, use it in this here. So it's not out of scope or you don't have to manually scope it. What that means, we'll see it over here. So code runs. First of all, read everything. Equivalent to stage and beginner. In the stage, there is beginner. So this is equal to this. All right. Stage beginner. This is equals to this. And the equivalent to roles student. So role is student. This is very much equal to role student. Now we are matching stage, which is this. All right. This data right. We are matching beginner and then we are printing beginner and we are matching advanced. Then if it matches, we print advanced. As for role, we are doing the same thing. Now what this use thing does is, let's say everything is printing normally like it should be. It is stage is beginner, so it prints students are role is student, so this one is printing. All right, everything seems to work. But what if we remove it from here? What happens then? What happens now? Does this code work? And no, then why not? See, beginner not found in this scope. So we don't know anything called beginner in this scope until and unless we used this. But we can also have a shorthand. We can, instead of doing, create stage and, making it available without manual scoping, we can use sort of manual scope. Like we can say that this is a stage beginner. Now this will run. This will run without any problem. No, this will not run. Why? I guess I have to also use create. I guess that's what I guess. It's a long list of error. So I guess I have to use sort of create. CRATE because I don't know what that create is, but let's use it. You still get many errors. Why? Why is that the case? Let's stage. Stage is equals to state beginner, so I shouldn't be toggling in this. Okay. Let's beginner be beginner. How about changing it over here? All right. So how about we make stage beginner. Will this work? I don't think this will work. We have to use so that we don't have to manually create everything. Beginner, beginner advanced. What happens now? It is saying stage. Is it capital? It's also capital S. How about now? Yeah, now it works fine. What about this? STAG. Ting ting beginner. This runs now. Why? Because of this. If we remove this back again, what happens? Error. Doesn't happen. Why? Because of these stage. I guess I'll get an error. Yeah, we get an error that not found in the scope. So to define it in the scope, we have to sort of create the stage manually over here. Now we have this in our scope. We have this in our scope, and now we can work with this freely. Or else, instead of doing stage beginner everywhere, we just declare it once and get free from doing this again and again. Beginner beginner. Now we don't have to do stage beginner everywhere. It works fine. And now what does this star do? It sort of takes everything from student teacher. Whereas in this bracket, we can either take one of the element from the enum stage. All right, and it works fine. Not works fine because there is no advanced right now. But we can explicitly say that there is something in stage called advanced. Now this will work. It works. Why? Because we can explicitly declare it in the scope, or we can just, you know, make it available to this whole scope instead of doing this back and forth again and again. So this is what the use is. Like we use standard memory, so we make it available for this whole damn code. If we use it like use, standard, very standard std standard, and then we say memory, then there is a standard memory in our Rust. But now, since we declared it explicitly, we sort of get it everywhere. What is it? Yeah, I didn't use semicolon. All right. Now, since I didn't use it, it is a dead code sort of, so it should show us some warning, but this playground does not show much of a warning. We have to use our, this environment to get a warning. Let's create to1.rs. Since so it's not very significant, we'll say Rust C and then 2.1. Yes, yeah. See how many warnings we are getting. Unused, advanced, never constructed, and then variant in this sum, in this enum. So born or dead, unused code. You're getting this, right? We just GCC. We might not get much of an error or much of a warning, I guess. Let's see. Yeah, still get a unused import, but we don't get a warning of dead code. All right. How about even stopping this unused int. How about doing this? Will it work? I don't know. I never tried this, but that's what we are doing, We are trying new things. Allow in the bracket. What is in the bracket? This is in the bracket. This. Will this stop our warning? Yeah, it stops our warning properly. Like no warning is there. So it's good. It's fine. It's wonderful. Good for us. So what next? So we now know this stops a warning coming in our terminal. See, we don't get any warning after using everything else. So we now know how to use what is alias and what are enums. We now know them. So let's move on to C-like. So enum can also be C-like enums. C, I guess it's referring to C language. So enums can also be C-like enums. And just again using this flag to not allow any dead code warning that we get. And then we are creating an enum called number, which is 0, 1, 2, element 0, 1, 2. And then there is color, which has element red, green, blue, red, green, blue. And then there's a main, which is trying to print 0. This is number 0, which is number and 0 as I32. All right, so as converts the type of whatever it has to I32 explicitly. This is explicitly doing explicitly. All right, so now this will have a value 0, one will have a value 1, and this roses will have, value of red in a hex code, and this will have a value of blue, which is in a hex code, and 6 digit of hex code only. So let's do this. Yeah, see this, we are getting hex code everywhere. And now what's actually happening is enum with implicit discriminator. What is this discriminator? So we have not, see, it's just English. It does not directly align with numeric 0. It does not. So what it does is, whatever, let's say we instead of writing 0, we write hero. It will take the value of hero as 0. All right, automatically. Think it of is like sort of index, but it is discriminating. All right, now it is hero, and hero has a value of 0. Why? Because it starts with a value 0. But let's say we assign a hero a value of 9, then this 1 becomes 10, 2 becomes 11. All right, it's discriminating, understand? Sorry, what happened? Not expected one of these. Hero equals to. All right, now so hero became 9. Let's make it 0 now. Hero became 9, and sort of 1 automatically became 10. It did not become 1. Now you understand what's happening. If you don't write anything, it automatically starts with 0. It's discriminating. All right, it starts with 0, this becomes 1, this becomes 2. It's a sort of discrimination. But as soon as it sees there is some number, it starts discriminating with keeping that factor in mind. So if it's 8, this will become 9, this will become 10. Let's say this is nothing, so this will start with 0. But let's say make it 5. So this will start with 0. But then what will happen is, this is 0, then this is 5. Then this becomes 6, because it keeps the data with respect to its mind, so that it can discriminate again. This becomes, how about using this over here? How about now? 1 is 5, all right, but let's say this is now 9. Will it come back to discriminating, or will it just accept our value? So now it will just accept our value, that is 5. All right. But if we don't mention any value, then it will have to discriminate for its own sort of expectations. What should it expect? So now it becomes 10. So you are understanding that it is trying to discriminate, starting with 0. And if it sees any pattern, it increments by 1 and 1, 1, 1. That's how it's discriminating. Same here also. So if red is, if there was no color, let's say no as a color, then no would have a value of 0. But since we gave a red a pattern of, this, so it starts discriminating based on this. Now, if we don't give green, or let's say we don't give blue a value, then what happens? It sort of starts discriminating based of this, and blue will get automatically value plus this plus 1. All right, let's see. Whatever this value is, plus 1. What is it? No. Why is that? Because there was no comma. Let's just add a comma, or we can just erase it. So violet, what became violet is just incremental of 1 from here. So it discriminates even in pattern. So it sees there is a hex code, and it discriminates according to it, and the discriminator then explicitly makes it plus 1. Now we are explicitly making it hex code, and the discriminator implicitly just add one to it. All right, and therefore we get this. It does not understand blue, violet, or whatever. Otherwise, this is the code FF, but we are getting this. All right. And when it gets the value, it does not discriminate because it does not need to discriminate. Again, one comma. Right. So this is what the C line discriminator enums whatnot. Enums discriminate if it doesn't see much of a value. It starts assuming stuff based on patterns, or based on no patterns, then 0, 1, 2, 3, and go on. And what we are doing over here using as, we'll see sort of in variable bindings or types, I guess we'll see that as is used to sort of convert explicitly something to something else, like I32 to U32 or back again. All right, let's move on. Now, test case linked list. So what is this? A common way to implement a linked list is via enums. So we now use create, not create. It's a create, and then create is of list, which is this. And we are making everything in this list available everywhere. So no boundation of, scope and all. What is this list doing? So it is CONS, which is cons, which means constructing a tuple structure that wraps an element and a pointer to the next node. So what it does is it is a tuple which has first of all a U32 value, and then second of all a box list, which is sort of a pointer to the next node. So it is pointing to itself only. List is list, and box is sort of pointing towards this list, and U32 is a unsized integer 32, which is always positive. And then there is another element, which is another type, which is nil, a node that signifies the end of the linked list. So if there is a linked list, this nil node acts as the end of the linked list. All right. Now there is an implementation of the enum, our structure list. What is it? Methods can be attached to an enum. So we are attaching some methods, like we are creating method called new, which creates an empty list. So there is a list which is starting from nil. So nil has a list type. So therefore it is empty. This is empty. Now we will prepend list. So first of all, it was empty. So there was, let's say, nothing. All right. And then when we prepend, let's say 3 to it, then it becomes 3 and nothing. Then we prepend, let's say 2 to it. So it becomes 2, 3, nothing. And we prepend, let's say 5 to it. And it's become 5, 2, nothing. That's how we are doing it over here. All right. So we are prepending it, not appending it. We are prepending. So consume a list and return the same list with a new element at its front. So now it is fn prepend. We are creating another sort of method called prepend, which first of all take the self. Self is list itself. And then we are giving it a element which has a type u32. And then it is returning us a list with some prepended value. How? We have we are using the construct, you know, that's why we used self, because we can use now construct, which will take this element over here as a u32 type and will then append it to the pointer of the list as new self. And box is getting the new self, new, and inside that we are passing this self. All right, so we are creating a new list and we are passing it as list back again. So pointer updates. So earlier it was like this, and we tried adding 3, or sorry, we tried prepending 3. It became like this, and we updated the list. It became like this, and then we sort of prepended 2 and it became like this. That's what's happening over here. Okay, now we return the value of the list. So we have another method which is length, which first of all take the self is list again, and returns a type u32 which is integer. Now what it does is self has to be matched, because the behavior of this method depends on the variant of self. And self has a type ampersand list, which is a reference of list, and dereference of self, which is again pointer towards list, has the type list matching on concrete type T is preferred over a match on a reference ampersand T. After Rust 2018, you can use self here and tail with no reference. Below, as we Rust will infer ampersand S and reference of the tail. See this link for more guide. Now we are matching the self, which is matching the list, and can't take ownership of the tail because self is borrowed. All right, self is borrowed. We can't just take the ownership, otherwise this list will get destroyed. And then instead we take a reference to that tail, and it's a non-tail recursive call which may cause stack overflow. So we are constructing it using construct. Oh yeah, we're constructing it, and we are then adding 1 plus tail dot length for the reference of tail. And base case is that this will return nothing, which is like list of element 0, length 0, everything 0. Nil will give us 0. We are matching the cons and nil that we described over here. We did not implement it, we did not do something with that, but over here we are matching it and using it. Now there's another method which is stringify. What it does is it takes the self, which is list, and then converts that into string, and then it matches the self again, and it constructs a head with the reference of tail, and then format is faster to print. No, format is similar to print, so it just does not give us an output in a terminal, but print does. Format just formats it and returns the value. So, but the returns a heap allocated string instead of printing it to console. Yeah. So format, now we are formatting it. We are returning a head and then tail.stringify. Why stringify? We made stringify somewhere. We made string, yeah. We are returning this function back again recursively, sort of. And then if it is a nil, we say format is nil. That's it. So we either return this string format, or we either return this. In case of construction, we return this. In case of nil, we return nil. In the main, now we are trying to create a list with our own defined uh, sort of implementation of list. We are saying mutation and sorry, we are declaring a variable list which is sort of mutable and of type list, which is predefined in enum, and we are taking the method new to get an empty list. See, empty list. Now we prepend 1 to it, and then we prepend 2, then we prepend 3, and we now have a list of 3, 2, 1 and empty. All right, as soon as it gets the empty, it knows that list has ended. Now it is show the final state of the list, so it prints the linked list has the length. What is the length? List dot length. We also defined it over here. Yeah, and then we are printing list dot stringify and whatever that string is. If there is head, tail, then that. If there is no list, we say nil. So at the end, we say nil. Before that, we are saying 3, 2, 1. All right. Length has 3 and linked list has the length 3. This is what's get printed. Now the test case, which is linked list. Let's move on to the next one, which is constants. It's going to, yeah, it's finishing soon. Now, constants are something like we can declare using const, which is const, but we can declare it using static. So let's first of all read this, that Rust has 2 types. Wait a second. So Rust has 2 different types of constant which can be declared in any scope, including global. Now both requires explicit type annotation. First is constant, an unchangeable value, the common case, and constant we all have declared it somewhere else. But constant is mostly written uppercase letters so that we know it. It sort of signifies that this is a constant. Do not change it or do not mess it up, or be careful around this. And same with the static values. So constant is an unchangeable value, the most common case. We have used it everywhere. As for static, a possibly mutable variable with this form. This is static lifetime, and the static lifetime is inferred and does not have to be specified. Now accessing or modifying a mutable static variable is unsafe, so we should not do this. And as for the lifetime, its lifetime is sort of inferred and does not have to be specified, because it lives as long as the program runs, and it dies as the program just dies or stops running. So it is sort of a lifelong declaration of whatever you are trying to do. It gets converted into binary and it becomes a part of program. It does not take heap memory or whatever like that. All right. So first of all, we are declaring static language, which is of type %str, which is Rust. So we are saying static, and that is Rust. We can access this Rust anywhere in the scope. Then we are declaring a const, which is of type, which is named threshold of type i32, and we are assigning it a value of 10. Now we don't want any magic numbers to appear, but if there is any hard-coded numbers, we mostly use const for that. All right. And function is big. There's a function called is big, and which takes a variable n of type i32 and returns a bool. So let's say if n, given the value of n is greater than threshold, if it's true, then we return true. If it's false, we return false. We return this statement itself, uh, or the equality of this statement. Like if it becomes true, we get true. If it becomes false, we get false. All right. What is threshold? Threshold is 10. And what is n? We'll be using this function somewhere. We are using this function and we are getting n. So now we are creating main function and using is big function in that main function. So before that, we are describing a value for n, which is 16, and it is immutable. Now we are printing that this is language. First of all, we are trying to access this Rust over here. So there's no problem with the scope. It works. And then the threshold is whatever threshold is, which is 10. It also works from here. All right. Then dash is dash, which is sort of n comes up over here, which is 16 is, and then dash is big. We are running this function is big and we are passing the 16 over here. So if it is true, then this is the condition over here. If this gets true, this gets true, we are getting this big as a placeholder over here string, or else we get the small over here. This is what that does. And then threshold is, we are trying to modify 5 and it does not work. So let's first of all comment it out so that we can run this whole program. So yeah, you see 16 is big. How about we make it 6? Then it will become small and we'll see small. And what if we try to, somehow we want threshold to become 5 now, but we can't do that. Let's see why. Now it says cannot assign to this expression. Why? Because invalid, left hand side of assignment, which is invalid in case of constants. And as for static string, we can also create something like mm, let name is equals to ALIC. Maybe sort of try to print ln this name. We must know that now this exists as a sort of static string, static literal. Commonly, we call it unofficially static literal or something like that. So ls, this is also a static literal. It also remains out of scope. So if we try to print somewhere over here, let's see, over here, will it print? Nah, name not found in the scope. So I guess we have to send it from here, but I don't want to. Still, let's do that. Maybe we get one more error. Yeah, so let's send it from here. N and NA. Now we shouldn't get any errors. Now we are getting an error. So type. What is the type of it? We are saying ampersand str, or we can say ampersand, static, static. But this will be a overkill, but works. Type is defined here, but on line 5, which is over here, you have to define it again. Ampersand str, but it is of type static. What else now? Annotated with lifetime here. What do you want? Should I not annotate? What? It's telling me to just remove this annotation of lifetime. It knows something is there. Now what is it? Invalid struct delimiter on fn call arguments. Is big name. Well, this is not a conditional, so yeah, it creates some error in, you know, if statement, because this can never be true and false, and we cannot make it condition. So let's not do that. It's creating some errors, some unexpected errors. But we now know it is a static string because it is. As for not creating a static string, that we have to do something like string, and then we say from inside this bracket we do something like that. Then we get normal string. What is it? Print name. All right, remove this. Yeah. So now this is not a very static string. This will remain in your heap or stack only. All right, let's move on. Now there's variable bindings. What is it? What does that mean? Let's see. So Rust provides type safety via static typing. Like variable bindings can be type annotated when declared. However, in most cases, the compiler will be able to infer the type of variable from the context, heavily reducing the annotation burden. Values like literals can be bound to variable using let bind. So let's say there is let an integer which is 1 of type your unsigned 32, and then there is a let a boolean which is true, then there is let unit which is empty tuple which is again unit type. Then we are trying to copy an integer into a copied integer, so we can do that very easily. There's a let copied integer, and then we are assigning a value of an integer to it. It gets assigned. Let's run it. Then we are trying to print an integer, which is the copied integer. In a debug mode, it will print. Then we're trying to print the boolean, print with it will be able to print, and then the meet the unit value, it will also be able to print. Now there is unused variable. So if you use any unused variable to silence those warnings, you must use the underscore, or else you will get warning. You won't see warning over here, but when we go to our environment and try compiling it, we'll see a warning if we don't use it. And this is a noisy unused variable, so this will create noise or sort of not errors but warnings that are not very pleasant to see. Let's create 3.rs. All right, now we'll get uh, two warnings. Why? Because this is also not underscore, and then we'll use underscore and all these warnings will vanish. Huh? Oh, $2. We have to compile Rust C $3. Yeah, see, we get two warnings. It says if intentional, then prefix with underscore. Like if you have intentional unused variable, then use sort of underscore before that, so that Rust knows that this is intentional. Otherwise, it will always send you a warning. So let's use it. Not here. Prepend it to the variable. All right, prepend. Now we won't get any warnings because yeah, that's how it works. So now we know how to shut up all these noisy unused variables. Let's move on. Now mutability. Where are we? We are in variable bindings. All right. So mutability. What is mutability? Mutability is the ability to change its value. So there is first of all immutable binding, which is one, and then there is mutable binding, and it is mutable because we have declared mut before that. So that is mute or mut. I don't know. Mute. So this is a mutable binding one. Now we are trying to print something like before mutation. A mutable binding is, what is mutable binding? It is one. Okay. Now mutable binding, we increment it by one and then try to print it again. What is now mutable binding? It is two. And if we try to increment immutable binding by plus one, it will throw us an error. We are waiting for the error. Yeah, see, immutable binding cannot assign twice to immutable variable. It has been assigned number one here, but we cannot assign it again. So we cannot append to the immutable value. So let's just remove this, run this, it works fine, right? We had one, and then after iterating it, we had two. But if we want a mutable binding that this one value has been used, now we want immutable binding to become two and drop that value one. What we can do is we can declare it from start, like again, and now it will not cause us any error. We can even print it. So if you want, we can even print it. It will show us two, or sorry, one. It was already one, but let's make it two, and then let's make it 10. No error at all. You'll say this is immutable binding. All right. Now we are seeing up. Immutable. So we are assigning or sort of reassigning this again, but we are using the let. All right. We are not incrementing on immutable bindings. We are then over here just dropping the previous value and let it assign a new value. That's what we are trying to do here. But if you say without using let, just increment the value to 10, this will throw us an error. All right, because you cannot assign twice. A immutable variable cannot be assigned twice. That's it. That's mutability for you. Now scope and shadowing. So now there is a main function. This binding lives in the main function. Then let long-lived binding is equals to 1. Now this is a block and has a smaller scope. This block has a smaller scope, and the main function is then the main function. All right, the main function is from here to here. Then it is trying to print the short-lived binding, which is 2, and then it prints it. But what we want to tell is we can also access the long-lived binding inside this scope. So if we say long-lived binding, we'll be able to access it. Inner short, we'll say inner ONG long. All right. Inner long, and then end of the block. We can get this value inside here, but we can't get this short level binding outside of this scope, because as soon as this scope ends, this variable gets dropped and there is no reference to what the short-lived binding was. So let's try to run. This will throw us an error because of this line. See, error. And as soon as we comment it out, but before that, just read this. So it says short-lived binding, and what it says is cannot find the value of short-lived binding in this scope. All right. So it means it is out of scope. How about now? Yeah. So this shows us inner short, which is this. Then this also shows us inner long, which is this value in this scope, and we also get outer long after that. So also variable shadowing is allowed. That means that let's say shadowed binding is, let's say, 1, and then we are printing shadowed binding inside this scope, which will work, of course. Then what we are trying to do is we are assigning the shadowed binding another value, sort of using let. This is very important. Without let, things will go wrong, definitely, because shadowed binding has some value to it. As soon as we assign it ABC, we are printing it in inner block. So we'll get the value is ABC. But as soon as this scope ends, this ABC value gets dropped. And what gets reassigned? 1. So now we have 1 as a value again. And we, as soon as try to print it, we get 1 over here. And then in this scope, in the main scope, we are then dropping this value of 1 and letting it have a new value which is 2 and then printing it back again. So everything works in this code. Yeah, everything works. Before, then shadowed ABC over here, then inner over here, and then this 2 over here. Everything works. Fine, let's move on. Now declare first. What it says is, it is possible to declare variable binding first and initialize them later, but all the variable bindings must be initialized before they are used. The compiler forbids use of uninitialized variable bindings, as it would lead to undefined behavior. Now it is not common to declare a variable binding and initialize it later. In function, it is more difficult for a reader to find the initialization when initialization is separated from declaration. Now, it is common to declare and initialize a variable binding near where the variable will be used. Now, we'll see it through this example. So, let's say there's a main function. All right. Now, we declare a variable binding over here, but we are not assigning it a value of 1, 2, 3, whatever. We are just saying there exists a variable called a binding. Now what we are doing is we are creating a inner scope, and we are we have a value x. We are creating a variable x which has a value 2, and now what we are doing is we are multiplying x by x, which is 4, and we are then over here we are initializing the binding which is 4, and after that the scope ends. So we must be thinking that now value will drop, but no, since it is defined over here, this comes under the outer scope variable. All right, so the value will not drop, but this x will get dropped. But this x's value, which was 4, is already in this a binding. So as soon as this inner scope ends uh, and we try to print a binding, we get the result of 4, and then we are seeing let another binding be a variable. We have not initialized it, and before even initializing it, we try to access its value. Since there is no value because it has not been initialized, it is uninitialized, we'll get an error. Let's see what that error will be. And then we are initializing it over here, and then we are printing it. This will work, but this will not. So let's see the error. All right. So it says used binding, another binding is possibly uninitialized. Yeah, that's what is the case. So it says just comment it out or remove this, and everything will be fine, and we can go to our good night's sleep. All right, everything is fine. Now freezing, how much is left? Let's see. What is static? Static is, see, this is static, in which we directly just say hello world. This creates static. We can't edit it. All right. Extern create, extern create RND. Well, quite interesting. We have not seen extern yet. We'll see it. I guess we will. We will see it. Let's close it. How about freezing? So what is freezing? When data is bound by the same name immutably, it also freezes. So the frozen data cannot be modified until the immutable binding goes out of scope. What does that mean? So we see it by an example. So there's a main function, and then we are saying let mutable integer be 7. Now it is of type i32. All right. Now in the inner scope, what we are doing is we are shadowing the immutable and mutable integer. We are shadowing by immutable sort of mutable integer. So let mutable integer be so see, it is right now not mutable. It is sort of immutable. All right. And then we are assigning this mutable integer over here. And then we are trying to, change this change this immutable variables sort of value. Let's get it by numbers. All right. So there, this is in outer scope. This is a mutable integer, which is a value of 7. All right. But inside a scope, we made another variable with the same name, mutable integer, but it is not mutable. Anna, don't go on its name. It's not mutable. Mutable, for it to be mutable, you must write it like this. Since it is not like this, it is not mutable. But what is the value of this variable right here? It is getting the value from here. So it is 7. So this is 7. And since it's immutable and we are trying to change its value to 50, it will throw us an error. And as soon as we comment it out, we are good to go. And then we close it out. We say mutable integer is 3. Since it is mutable outside this scope, this is mutable. So this works. But inside this scope, this is immutable. Inside this scope only, because we have not said immutable. Let mut be. Now, because of that, we'll see an error. Let's see. See, we are getting an error. So to solve this, either we should not, assign it a value of 50, which will fix it. And another way to fix it is, see, no output means it has been fixed. No output means no error as well. First of all right, we'll make it mutable inside the scope also. Now this works. Or let it be mutable. Since it was already mutable, no need to reassign it and change its value. So it works. No. All right. So this is what freezing is. If we made it immutable inside the scope, so inside the scope it has freezed. Now it is not mutable, so that you cannot change it according to your own will. All right. Let's move on. Now there are types. What are types? So Rust. Oh, it came up to different. Oh, so we are on 5. All right. There are 4 topics remaining, and then inside this there are 3 more. So approx 7. So we'll take a break for 2-3 minutes, a water break, something like that. All right. So we have types. So Rust provides several mechanisms to change or define the type of primitive and user-defined types. And the following section covers the casting, which is between primitive types, specifying the desired type of literals, and using type inferences and aliasing types. Let's see each of them. So casting. What is casting? So now Rust provides, well, this is again very long sort of code. All right. So casting. So Rust provides no implicit type conversion, which is coercion, between primitive types. But explicit types like conversion casting can be performed using keyword as. Yeah, that's what I hinted at. You know, few lessons back. So yeah, like from decimal, I can create it using as. I can create keywords. All right. So let's see. So Rust provides casting with which is sort of explicit conversion, uh, which we do it in, by our own will. Rust does not does do it for us. All right, so it's not implicit; it's explicit. Now, rules for converting between integer types follow C convention generally. Like except in the case where C has undefined behavior, the rest works fine. Like C. The behavior of all cast between sort of integral type is well defined in Rust. So we sort of not allow the overflowing literals, burning from that. And let's see each of these one by one. Before that, just delete the rest of it. So let's see this. So we have a main and we have a decimal, which is 65.4 and 321 of type F32, which is sort of how many bytes? F32 bits. So in 3 divided by 32. 4 bytes. All right. So this is float 4 bytes. Now in integer, we cannot do this. Like we cannot say that, hey, integer, it is of type U8. So decimal value gets assigned to integer. This will throw us an error. Let's see. This must throw us an error that we will see. Yeah, so it says there is an error. U8 is expected due to this U8, expected U8 but found F32 because decimal is of type F32. All right, was found this integer value expected U8, but since we are assigning decimal value to that integer, we are assigning it something near F32. So what we can do is instead of doing implicit conversion or thinking that implicit conversion will happen, which it doesn't, we use as keyword. So we say decimal as U8. All right. So we convert this decimal from float 32 to U8, which is unsigned integer of 1 byte. And then we assign that value to this integer. And then we convert this integer's value as character, and then we assign it to a variable character. And then what happens is we get sort of a chain where we are using decimal, which is 65.4321, and we are getting an integer, which is, decimal, which is 65, and then we are converting the 65 to character, which is capital A. So that's what is happening over here, casting dash dash dash. What was happening in this line that I commented out? I was seeing something like decimal as character. So decimal is F32 and it cannot directly get converted into character. Why? Because character can only require U8. So it requires U8 can be converted. So it's you see the error. Only U8 can be cast as character, not F32. That's the error in this line. All right. So from decimal to character, you cannot directly do it. You have to go through integer as U8, and from that integer, you can do this character. All right. So this much code is, I guess, fixed. So let's delete it since we understand what was happening over there. We used as very extensively. All right. Now over here, when casting any value to an unsigned type, which is t, and t max plus 1 is added or subtracted until the value fits into the new type. All right, 1000 already fits in U16, which it does, and 1000 as a U16 is sort of 1000. Let's print it one by one, shall we? And for that, let's do this on the end of the page. Uh, let's do this. So, and we run this alone. Uh, I think the commenting has some sort of problem. See, 1000 as U16 is 1000 only. All right. Uh, but when we do something more complex than just 1000, like, but 1000 as U8, so we halved the byte. So it was 2 bytes. Now it is just 1 byte. So now what will happen is it will overflow. 1 byte can have 256, 0 to 255 elements. So that is 256. And then we are going it like if there is a bucket, all right, and it is filled with water. If we fill it with more water, it will overflow in a different manner. But this is a different sort of overflow. This is not bucket overflow. So let's say there is a bucket of size, 256, and if we let the tap remain open, what happens is the bucket is always filled up to 256. All right, it doesn't become 242 or 236. All right, but over here what happens is as soon as you hit the 256, you go back again to zero. You start from zero. So this is a sort of cyclic bucket or some sort of overflow in a cyclic manner. As soon as you hit the zero, you restart. You hit the zero, you restart. uh, it is like a skipping rope or the timers. You got timers now. As soon as you reach the end limit, you start. All right, the counter, the clicker counter. So this is what this overflow is. That's why we are minusing 256 as many times as needed, like 3 times. Then we are getting only 232, which is not greater than 255. So it's not overflowing. So now that is why we are getting the 232 as a value over here. See, 232. All right, so let's see this. Under the hood, the first eight least significant bit, which is LSB, are kept, while the rest towards the most significant bits, which is MSB, gets truncated. All right, now let's move forward. Now what's happening over here? If there is -1, so let's say if it reached the ending index, that is 255, then it started from, let's say, 0th index. But if something was already at 0th index and we minused 1, what it will do is it will reverse the flow. So instead of going, forward, it will move backwards. So from 0 directly comes back to 255. All right. So that's what is happening over here. As we try to print -1 as U8, it directly jumps back to 255. So we see 255 if we run it. Hmm. So we see 255, and now we see another thing. For positive numbers, This is the same as the modulus. So if uh, what is modulus? Modulus is sort of the remainder that you get. You know, in division, let's use Python. So in division, you either use 1000 divided by, let's say, 256. What do we get? 3.90. So this is a question. All right, and it's happening in a float value side sort of thing. But if we want to know what is the remainder while dividing it and not fully dividing it, so it's something like 232, exactly what we would expect. So if we do 1000 mod 256, which is equals to this, we will get 232. All right, 232. Now we'll remove all these codes. Now when casting a signed type, which is the bitwise result, is same as the first casting to the corresponding unsigned type. So if the most significant bit of the value is 1, then the value is negative. Like the unless it already fits, of course. So let's say it is 128 as a 16 bit sort of, you know, it is on sort of benchmark. Let's run it. Oh, 16 bit. Yeah. So 128 is on the brain, so it is 128. As soon as we do 129, what happens? Nothing, I guess. Something interesting. 128. What about one? Oh, we didn't do anything about 129 over here. 129. I16. I16 means 2 byte. All right. 129. Unless it's already fits. So it already fits, so there is no problem. But if we half the size, like now we do it I8. So now it is 1 bit only. Sorry, 1 byte only. 8 bits, 1 byte. Now this does not fit. So what it does is it does minus 128. Right? So it's overflowing, underflowing, whatever. So in this boundary case where 128 in 8 bit, 2's complement representation is minus 128. So that's what's happening. Now we are trying to represent some example above. So like 1000 as U8 is 232. And 1000 as U8 is 232. Now 232 as I8 is, what is it? 232. Always 232, I guess. Now the value of 232 in 8-bit 2 complement representation is minus 124. All right. As soon as it became signed integer 8-bit, it gave us a value of minus 24. So let's first of all remove these, and we'll get something interesting. So 232 as I8 is minus 24. 1000 as U8 is 232 as expected. But now it is becoming interesting. You can see all these values change in real time by yourself. You can discover something really interesting about overflowing and memory, all that. Now what's next? So since the Rust 1.5 as the keyword, since the Rust 1.45, the as keyword perform a saturating cast. When casting from float to integer, if float point value exceeds the upper bound or is less than the lower bound, the return value will be equal to the bound crossed. All right. And the 300.0 as U8 is 255, which is interesting. Right. We are defining it type over here. We are converting into U8. We are printing it. Exactly right. Now, what's next is we are seeing minus 100 getting converted into U8, which is float 32 to U8. And then we are seeing the NaN value, which is again float 32 in this type, but we are converting into U8. So let's see. So minus 100 becomes 0 and NaN in U8 also becomes 0. Now this behavior incurs a small runtime costs. So this behavior incurs a small runtime cost. What happens before because of it is with unsafe methods. So however the result might overflow and return unsound values, like this does not sound very good because minus 100 is 0 and is 0 because we are trying to compress 16 bit into 8 bit. This causes some unsound values and use these methods wisely. So this is unsafe because 300 as U8 is now 44. So we are using to int unchecked and then converting it instead of using as keyword. Same with 100 and same with NaN. And we should get 0 over here and with minus 1, 156. Let's go. Yeah. So we see the defined value. So I think we completed this. Let's move on. Now literals. Well, let's two more. All right. So what is literal? So numeric literal can be type annotated by adding the type as a suffix. So what is it? The numeric literal can be type annotated by adding the type as suffix. As an example, to specify that literal 42 should have the type I32. That is write 42 I32. All right, we can do this. It's all right. We can add type as a suffix and it works. It's not weird. Looks weird at first glance. It looks more complex than the number itself. But yeah, it's important. We know that 42 is now a signed 32-bit integer, which is 4 byte. Alright. Now the type of unsuffixed numeric literal will depend on how they are used. If no constraint exists, the compiler will use I32 for integers and F64 for floating point numbers by default. If there is no constraint, all right. So let's say X is defined as U8, Y is 2, value is 2, and it is also U32. Z is a 3, which is float point 32. All right. So now suffixed literal looks like something like this, and their types are known at initialization. So as soon as we initialize it, we know their types. But sometimes we don't. Like we say let I is equals to 1. Now what will be its type be? It can be I32, it can be I8, it can be U8. What is the type of I? Alright. And what is the type of F? It can be 64-bit, it can be 32-bit. So to see the sort of size of value returns the size of variable in the bytes. So we use standard memory size of value and we are passing every variable by its reference and we see how many byte it takes. So now we see that X in byte takes only 1 byte because U8 is sort of 1 byte. U32 is 4 byte. Then F32 is again 4 byte. As for I, it is not, suffixed. Yeah, it is not, it has not, no suffix type. So it is already implemented as I32 by default. and the float was given F64 by default, which is 8 bytes. So yes, this works. Now we know either we can initialize it and give it a type, or we can just leave it initialized and our compiler will give it a type. Now, there are some concepts used in previous code that haven't been explained yet. Here's a brief explanation for some impatient readers, but we are very patient readers. So we'll just go through them and not go to these modules or crates. All right. So there is standard memory size of val is a function, but called with full path. And code can be split in logics. So unit called modules. In this case, the size of val function is defined in memory module, and the memory module is defined in standard crate. So for more details, see the module and crates that we'll be seeing in future over here also in the 11th. All right. So be patient. Now the inference. The type inference engine is pretty smart. It does not it does more than looking at the type of value expression during an initialization. It also looks at how the variable is used afterwards to infer its types. So here is an advanced example of type infer. So let's say there's an element that has a value of 5, which is of type u8, and now there is a mutable vector which is of vector and type new. And what is happening is, because of the annotation, the compiler knows that element has type u8 and the create an empty vector a growable array. So looks like this. At this point, the compiler doesn't know the exact type of vector. Like, it just knows that it's a vector of something, does not know what. So as soon as we push the element which is of type u8, all right, insert the element in the vector. Now the compiler knows that vector is of type u8. To do is to try commenting out this element line and try printing it. So this will obviously throw us an error because we have not initialized this vector yet. This vector does not know what is the type of it and what is the size of it. All right. So this works, but as soon as we comment it out, we see some errors. So this is right now a 5, which is of type u8. Let's see as soon as we comment it out, what is the error. So error is type annotation needed for vector to be initialized. Type must be known at this point over here. Help is that consider giving vector an explicit type, where the type is sort of type parameter t is used. So what if we try using, vector is of type t? What happens now? Error. It will have an error. Not found in the scope because t has not yet been defined. Yes, we know. What if it is by default u8? All right, now it knows. So uh, expected u8 found vector. All right, so not over here. We'll define it inside this. This is type u8. Not a value. Yeah. How to pass this type u8? Since this is not a topic out vector, this is topic out win interest, so does not explain it in great length. But expected expression. So I guess we have to do something like this only. On a vector which is type u8, which will work. No, it will not work. And let's move on. Use double colon instead. So path separator must be double colon. Ambiguous. Like if there were trait name example with associated u8 implemented for vector, then this would be the thing. All right. Now aliasing. We all know what aliasing is, I guess. But let's see here. All right. So we are aliasing U64 to a type using type to a nanosecond. So nanosecond is of type U64, inch is of type U64, and U64 is of type U64. So the type statement can be used to give a new name to an existing type, but the type must have a upper camel case, all right, name, or the compiler will raise a warning, not an error but a warning. Upper camel case, so looks like this: nanosecond, inch, U60. All right. The exception to this rules are primitive types like U size or F32, etc. Now, main nanosecond is equals to inch is equals to U64 is equals to U64 because it essentially is U64. We are just using it as aliases. So now let inch is equals to 2 as U64. So there is no problem with that because it is ultimately U64. Now note that the type aliases does not provide any extra type safety because aliases are not the new type. So we are not defining a new type called nanosecond, inch, and U64. We are just aliasing the U64 to a more fancy name that is nanosecond, inch, and U64. So it is not a special or new type. It is just an alias of an existing type. So therefore, it does not provide any extra type safety or anything like that. So nanosecond is also, 5 inches is 2 and unit is 7 unit. So everything works. Why? Because everything is essentially of type U62. Now, the main uses aliases to reduce boilerplate. For example, the IO result T type is an alias for result T and IO errors. All right. Now conversions. So this is, I guess, sixth module. Shall we start it? No, I guess this is lengthy, so we'll take it another time in depth. So from into to two and from triform to triumph. So conversions are important because if there is any errors, it will raise some, good content errors. So I think we should